So what we're doing today is, what we're starting with is NumPy, and I'll of course be sharing this notebook with y'all through GitHub. It's not in there yet because I've got to build the rest of it for y'all, right? What we're talking about today is NumPy, and I've got a link to the documentation, and specifically in the documentation for y'all a link to the quick start. Okay, so this will help. So that's what we're doing. Well, so what? Why should you care? Why should you care about a specific Python library? Number one reason, folks, NumPy itself, it is 25 years old this year. If you can believe that, that's wild. NumPy started as a project in 1995 on top of Python. It's written in Python, but NumPy itself is one of the main driving reasons why Python is so powerful and popular, specifically for scientific computing. Not just machine learning, not just data scientists, not just data science, but science, right? There's a lot more scientific analysis on planet Earth going through Python than many other languages, right? And NumPy is one of the main driving factors. Why? So that begs the question, why is NumPy so popular? Well, the answer is that it's super fast. It is super fast. And I'll give you all a demo of that first thing when we start the code in like 1 minute, 2 minutes, right? What's going on underneath the hood with NumPy is that the NumPy arrays, and when I say the word arrays, think in your mind lists. That's it, right? Arrays are lists. They're ordered sets of values that are finite. Right? We don't have an infinitely long array or an infinitely long list, but arrays are just like Python lists conceptually. They're a little different. They have many more capabilities. NumPy arrays have many more capabilities. And for the mathy folks in the audience, or any folks in the audience, because hell, you're in a data science class, you're a mathy folk to me now, right? An array is a vector. So if you ever encounter the term vector in any kind of like linear algebra setting or anything, vectors or matrices, NumPy is where you're going to be doing that work. So these NumPy arrays, that was a lot to talk about, just one word, array, right? But our NumPy arrays are implemented in the C programming language. Now, this doesn't mean that you have to learn the C programming language. In fact, all you got to learn is Python you already know, and some of the, certainly not all of the capabilities of NumPy, because it's huge. But I'd say we're going to focus on like the 5 or the 10% of the commands that you're going to use 99% of the time. And so you don't have to learn C, but because NumPy is not talking always straight through Python, sometimes it's going straight through C, it means NumPy is very, very fast, right? Very, very fast. We talked a little bit about that big O notation yesterday, right? The number of operations that a computer has to do given the number of elements in a collection, or the number of the amount of time it takes for an operation to complete. Well, NumPy is darn fast. So I'll prove it to you in a moment. It's also our linear algebra library in Python, right? If you wanted to work through like a linear algebra textbook or something like that, my advice would be read the math, but do your work in NumPy, because all of our linear algebra functions and transformations are available in NumPy, which is, again, why it's one of the most popular scientific libraries on planet Earth. 2 things that I think will help y'all immediately with writing code that's, 1, it runs faster, and 2, code that's easier to think about and reason about and literally easier to write, is with NumPy, and this is going to apply to pandas too. These arrays provide loop-like behavior without the overhead of loops or list comprehensions. And what we're talking about there is vectorized operations, and I'll give you a demo of that. Another feature, but wait, there's more, right? But wait, there's more. NumPy provides the capability for doing the same work as operating on a list with a loop with a conditional. So you don't so with NumPy, we can do things very easily. We can have very clean, very easy to read one-liners instead of a loop looping across a list with a conditional in it or two. So it means we're going to have more concise code, and I will argue that that code is actually easier to read than in NumPy. And I'll show you a demo of that. So that's why we should care. NumPy is a big deal. Certainly a library you want to put on a resume, or a library you want to list on LinkedIn as a skill, right? Starting after these exercises. And we'll be using NumPy and its conjoined twin pandas together the rest of the course. And then we'll be visualizing these data structures with Matplotlib and Seaborn, and we'll be doing this over and over and over and over the rest of the course. These four libraries: Matplotlib, NumPy, Pandas, Seaborn, because we can't just jump straight into any machine learning unless we clean our data and get to know our data, right? So now what? Is we're going to start working with NumPy arrays, and I'm going to show you various ways to create arrays. Various ways to create arrays. Sounds like a song. Once we have a NumPy array, what's really neat is we can run functions on there, or methods rather, like min, max, median, sum, standard deviation. The way to call median is a little different because we have to call it off of NumPy, the NumPy library rather than the array itself. But I'll explain that difference in a little bit. I didn't finish my sentence here, or maybe I did. Learn to use some. Learn to use some NumPy. So let's see. Learn to use some vectorized operations, which is easy. It's dang easy. There's not a lot to learn there. You just do it. And then learn how to create arrays of Booleans to filter results. That's what we're doing. This is our roadmap here. So you may be wondering, Ryan, how do I use NumPy? Well, you start with the imports. It is customary across the industry, and you'll see, and not just in our code, but in other people's code, in books, and in other code, that we import NumPy and then alias the NumPy import as NP. You don't have to alias it, but it'll save you keystrokes, and most people do. All right. So we've imported NumPy, which means we now have access to some of our NumPy functionality. And the first thing that I want to do to prove our speed result here, I'm going to clear out my kernel real quick. Just restart the kernel. We'll import NumPy. It's nice and fast. There is this helper, this kind of magic function in Jupyter Notebooks and IPython. It's %% time it. And what this will do is time, it'll run a specific cell of code, like a number of times, like 7 or 8 times, and then it gives us the average of the results. So what we're going to be doing to make a time it, I'm going to make a range of the numbers from 1 to 1 million, and I'm going to square every number. Fairly straightforward operation, but I'm squaring every number in that range. So I'm going to run the cell in base Python. Hey, 370 milliseconds. Boy, that's fast, right? Well, check this out. Three milliseconds. So when we're looking at how much faster NumPy is than base Python, we have 370 divided by 3.04. And so we see that for this operation, squaring a million different numbers, NumPy is 121 times faster. Not bad. Not bad, right? Python itself isn't the slowest language in the world, but NumPy to be, so you'll see this factor change on different operations. NumPy's dramatically faster at some operations. It's double the speed in other operations, but 120 times faster that's jaw-dropping, right? So can keep that in mind. Keep that in mind as far as like why NumPy. Okay. So I want to take a moment and pause and prompt and see what questions y'all have so far. I guess on the conceptual part of NumPy, and also on the rationale, or if there's anything that's a burning question before I dive deeper into specific code.
I guess, what's the reason why C is so much faster in doing computations than Python?
Yeah, that's a really good question, David. So the answer comes down to C is what we call closer to the metal, right? So when I say close to the metal, what I'm talking about is how close is your programming language to the processor itself, because every single programming language is running in a way where it converts its directions into a set of operations that exist on a processor. So processors have a limited set of operations, right? The processor itself doesn't have the time it function or the sum function, right? Your processor itself has, heck, I think Ken would probably be able to do a pretty good dissertation on how processors work, right? If I recall correctly, Ken was working in a semiconductor, or is that correct?
Yeah, but mostly just working on the machines that make them.
Oh, I gotcha. Cool. So yeah, processors are running a small set of instructions, and you may see stuff in the marketplace that's like, Apple is coming out with a new processor, or has already delivered this new processor called the M1 chip. It's supposed to be faster, yada, yada, yada. So people are looking at ways to make processors faster. But all of our programming languages have to convert the instructions into the machine code and the processor instructions. And so when I talk about close to the metal or not, I'll just put this in my notes. C is closer to the metal than Python. Assembly is closer to the metal than C, and processor instruction sets are the metal. Right. So if you ever hear, oh my gosh, Python's so slow, what's going on is Python is literally written in the C programming language. The C programming language is literally written in the assembly programming language. And assembly goes back to like early 50s, I want to say, if memory serves. And then what is assembly written in? Assembly is written in the processor's instruction sets. And so there are actually like little different versions of assembly based on different kinds of processors and processor instruction sets. So one of the really wonderful things about Python is that the designers of the language said, here's all this other stuff in other programming languages that drives us bananas, and like, and I'm not going to go into every little bit here, but Python's very flexible, right? And our learning curve with Python has been pretty approachable compared to C, right? If we were focused on C, I mean, good heavens, we need about 6 months in C to catch up to where we already are in Python, is my best guess. Right? It's just, there's more to learn. It's a harder language to learn. There's more pieces, more to keep track of. You literally have to manage the memory of every operation yourself. So one of the upsides to that is C is real dang fast, right? One of the downsides is, well, Python is a friendlier language, but it's not as fast as C. So C, like the C programming language, is running on like internet connected toasters, and C runs on a lot of devices, and but yeah, this is kind of the food chain. And so what the original designers of Python did was they created things like lists and tuples and dictionaries, all the data structures we've seen so far. But the folks who developed NumPy said, hey, if we connect to C directly, and if you look at the code for NumPy, there's some Python code that talks to C, and then there's a bunch of C code that does the job of working with these arrays. So that's how we're able to produce results that are 120 times faster. Yeah, that's a good question, awesome. David. Did that answer that for you?
It did, yep.
Awesome. Any other questions right now before we get into making some actual NumPy arrays? If y'all are good, we'll keep going. Okay, let's keep going. So let's make our first NumPy array. And here's how we do it. Let's say that you have some collection, like the list 1, 2, 3, 4, 5. And the type of that is just a basic Python list, right? How we make a NumPy array is we do the NP, because we have to talk to the NumPy library, np.array, and then array is a function that takes in an argument, and it converts that list into a NumPy array. So let's run through this, and I'll print out, we'll print out X, and then we'll print out the type of X next to it. So we have an array. The data type is no longer a basic Python list. We have a NumPy array of these values, and then the data type itself identifies as NumPy array. And then this ND array, it's not a typo. The N and the D here stand for n-dimensional array. So we can have multi-dimensional arrays in NumPy, and they are it's built from the ground up to be able to handle multi-dimensional arrays, right? So that's what the ND stands for. It's not a typo. It's not non-disclosure. It is n-dimensional. So I'll give you an example of the dimensions. Let's check this. Let's check the shape here. Yeah, shape. So shape tells us shape is a property, not a function, as we saw. Shape tells us the shape of our n-dimensional array. And this is just a list of or just a single dimensional array. I did mention that we can have multi-dimensional arrays or multi-dimensional vectors, which is a matrix, right? And so what I'm going to do for my happy little matrix here is we could say np.array of the following list of lists. So a list of lists is a two-dimensional product. It's a two-dimensional item, object in the world, right? And see, we have an array of arrays, and the data type of this array of arrays is still ND, an n-dimensional array. So with NumPy, you can work with arrays or arrays of arrays or arrays of arrays of arrays of arrays, right? And NumPy is just going to chew them up and do whatever you need. The very nice part about NumPy array syntax is that we can use all of the tools or the basic tools we've already worked with, like the array or the list index syntax, right? List index syntax works on NumPy arrays. So we're accessing the first element of this matrix, and that first element of the matrix is itself the array of 1, 2, 3. Okay. If I wanted to get the first element of this first array, matrix bracket 0, bracket 0. I'll pause here for questions because we just went from 1 dimension to 2 dimensions, and that's kind of a big deal.
Line 16, or sorry, in 16, that one could have been 0, 0, like a coordinate.
Well, thought for the day. Let's answer questions experimentally. 0, 0, like that?
Yes.
There we go.
And it's row column. I'm trying to get the understanding of the 2 brackets.
Oh, the 2 brackets on 16?
Take it and do 1 and assign it to a variable, and then do another, and you'll see exactly kind of how it's doing that. Exactly. Yeah, so just think about it as in Amanda in matrices as you would like selecting I comma j or whatever. So you're always going to have the row first and the comma and the column second, but you can do it as like you first select the row and then it's returning an element, right? But you're not actually returning it. You're just using that element to then select as you could think about it as the column.
Cool. Did that help, Amanda?
Yes. So, I mean, we can use the syntax interchangeably.
Oh, the positional syntax with the commas, or the list access syntax?
Correct?
Yeah. Yes, that's a true statement. And that'll remain if we had a 3 or a 4-dimensional array, NumPy array. It'd be the same. We'd just extend things out.
So just messing with this, Ryan. So if you go outside the index, it returns an index error, and it tells you you're out of bounds. So that's when you know that you've gone too far.
No, you're out of line. Yeah, and that'll happen in any programming language. If maybe not every programming language throws an error. Some give you back like a -1, which is nonsense if something's not there. But like if you try to access something that's not on the list, you're going to get an error, right? Like a negative index, you'll get an error, or an index that's too large, you'll get an error.
So what does it mean when it says access 0 with size Z, or with size whatever you've put in?
Oh, the AXIS, the axis?
AX, yes, yeah.
That's rows or columns.
Just another term for it.
Yeah, rows or columns. Absolutely. So we can also, let's see, I think I had an X here. We can also use our range, or not our range, but our splicing syntax. So if we went from 1 to 3 on this array, So I'll say the entire array on the left. That's our entire input array. And then the range from the after the first element up to, but not, let's see, 1, 2, 3, up to and including the third element. So we can get subvectors of our vectors here, right? With this colon syntax here. All right. And this all came from taking some sort of Python-like structure and turning it into an array with np.array. So we converted basic lists earlier, and now I could do a range here, and I'll make my variable called a, right? So anything that is a list in Python or list-like a range, gosh, what else have you all encountered that are range-like structures that are iteratable? Anybody have a memory of something that kind of works like a range, but isn't a list? It is loopable, but it is not a list itself. Maybe one of those collections from the permutations and combinations library. Amanda, I think I saw you unmute.
I was going to say dictionary, but now I'm thinking otherwise.
Yeah, we could. Yeah, we're probably not going to take dictionaries and put them into NumPy arrays, but what we could take the values from dictionaries and do that. Yeah. And when we have a multi-dimensional array or a matrix in NumPy, we have rows and columns. We just don't have labels, right? So, awesome. So this is really our workhorse is np.array. And what this gives us, so let me make sure I'm following my own pattern here. What this is going to give us is we can do things like sum. We can do things like mean. We can do things like xmin, xmax, functions, standard deviation, right? And we'll just put those out real quick. Right, so that's not too shabby. So that's x. Let's do a because I just made a. And I noticed some of y'all on your 101, like on some of those functions, I noticed a handful of folks imported NumPy to help out or imported some other libraries. So that's pretty cool. If we wanted the median is different. And there's some other methods that work. Functions that work similar. If we wanted a median, we would do np.median of our array. So, hey, look at that. The median of the numbers 1 through 99 is 50. Go figure. Okay. You're going to see this the distinction that I'm trying to call to your attention is a whole bunch of these functions, a whole bunch of these methods were run with a dot notation off of the array itself, right? And this mirrors a lot of what you've seen with like Python built-in list operations. But every so often you will see a specific function that you've got to call off of the NumPy library itself. And median is one of those. And you'll notice that the way to create a NumPy array, we call that straight off of the NumPy library itself, np dot. So you'll start to see a couple more of these, but don't let that trip you up. Worst case scenario, if the here's your decision tree. If the method doesn't exist on the array, it'll exist on the NumPy library. And if you can't find it on the NumPy library, check the docs, right? Check the docs. And I've got a link to the docs at the top of here.
Hey, Ryan, is there a reason why it defaulted to 17 columns for that array?
I don't see any columns. I see the print. I see what you mean. Visually, there are columns here, but see that there's only one set of square brackets. That means that we have a one-dimensional array.
Yes, I see that now. Thank you.
Yeah. So yeah, if we're talking about rows and columns in the data structure itself, because this is just a display, right? If I crunch my display up, the word wrap changes, right?
I'm not too sure if I was supposed to import anything else, but whenever I tried running cell 24, I got an error. It says numpy.int64 object has no attribute A, but I already ran your cell 22 as well, so I don't know why I'm right. Yeah.
Has no attribute. That sounds like a data type issue. Your input doesn't have any strings in it, does it? It's just numbers.
Yeah, I typed down, I'm double checking. I don't see any typos. Because I got the same array out as you did. And then whenever I went on to cell 24, I got that error.
Are you missing any commas in cell 24? If you want to paste your code in like Slack or something, or I'll take a look at it. And see.
Oh, you know what? You're right. I think I accidentally put a period. I'm so sorry. Yep.
Okay. Cool.
My bad.
No worries.
Good catch. Thank you, Maggie. And yeah, Amanda, like gold star for asking the question, right? Because I want to incentivize not just getting right answers and things running perfectly, but just taking a swing at things, right? So gold star sticker.
I think I just kept on a dot and yeah, typo. My bad. Thanks.
It's okay. I've introduced this comma output on purpose today. I don't think y'all have seen this a lot so far. You may see this moving forward, but I'm showing like 5 things on one cell, and actually see how the cell has parentheses. That means that this has created a tuple for us, but it's just a way of getting everything on one cell for me. All right. I'm going to give you because we're talking about a little bit about the indexing, and I'm gonna touch on something. Let's say we have some array that is 2, 3, 4, 5, and then we have another array should include elements, and this itself can be an array. Let's say we don't want 2, we do want 3, we don't want 4, we do want 5. So I'm making 2 different arrays here, and here's what I'm trying to demonstrate. If we take a specific array and use another array with trues and falses, we can filter our results. Check this out. So what's going on with this array of Booleans here is we are saying at each corresponding index of the array that's called B, turn on or turn off that element. And if we have any trues in here, then we end up turning on those elements in the output. Because trues are ons and falses are offs, right?
Would that work with a 2 or 3 dimensional array where it'll just return each matrix index and just those 2 values?
Yeah, like if I had another array right here, like that.
Yeah, or like how you did it before where you had I guess 1, 2, 3, and then another list 4, 5, and 6. Yeah,
Absolutely. We had that matrix earlier, right? And I couldn't turn on or turn off a 3-element matrix with a 4-element Boolean array. But we could do, give me the first row, not the second row, and the third row. Excuse me, let's see. Should include the elements. The second and the third. My tab autocomplete is being weird today. But yeah, we can turn that on. And if our Boolean array, this is more detailed than we'll go into like manually, but if you had a Boolean array of Boolean arrays, we could slice into, yeah. Was that where you were headed?
I thought it would actually give a 3-dimensional array, but then return the second and third values in each list. But this makes sense as well.
Each element is another array itself, so we only allowed back in two arrays.
I'm glad I saw it because now that makes sense the way it ran it.
Awesome.
Yeah, that Boolean, whenever I was reading that last night, it made 0 sense to me because I didn't realize they were referring back to because I had it like printed out. And so I didn't look further back up at it.
Yeah. This is a big deal. Arrays of Booleans, these are the beating heart of filtering and transforming arrays. This is how we can do loop-like stuff without loops. Right? One of many different types of doing loop-like behavior without loops. All right, so I'm going to give, let's see. Yeah, I'm going to give y'all some more examples of this array of Booleans. Arrays of Booleans are gigantic. They're huge. In NumPy and in Pandas. So let me give you another example. We kind of hard-coded this stuff, right? But let's say I have some variable called x, and I'm going to make a NumPy array. That's 1, 2, 3, 4, 5. Right? And if we were to say, hey, x, which of your indices contains the number 3? What do our comparison operators always give us back as a data type?
Booleans.
A boolean. Great place to start with a soup is with an array of Booleans. So we get back, hey, yes, I do have a 3 in here somewhere, right? What if we said x is less than -9? So it's going to be a negative number that's less than 9. There's nothing in there. It's all falses, right? How about x is something maybe a little more, just one more, x is greater than 3. So 4 and 5 are greater than 3. So we have these corresponding indices. Now check this out. Whatever we do to produce an array of Booleans. And it could be more complex than just a greater than, a less than, or an equal to. It could be something like x divided by 2 leaves no remainder, right? Remember that modulo operator. So we have a true everywhere where there's an even number here, right? So check out what we can do. X, and I'll start with the first example. What we're doing here, there's a name for creating an array of Booleans like this and using this array of Booleans to filter our results. This is this spell, if you can call it that. It's called Boolean masking. And folks often, folks might say array filtering, or something like that. So let's do an example of Boolean masking. Now that we have these trues and falses, just like the example above, we can combine the array. So I'm going to make a mask here. I'll say only 3s. So my mask is x matches 3, and then I can say x where there's only 3s. And see how this filters out everything that's a false. Every number that had a false for if it's 3 or not does not make it to the promised land of the output here. It's filtered out. We don't need the extra variable. We can do the following. We can do x where x is equal to 3. So I read this code almost like SQL in my head. Select x where x is equal to 3. I'm kind of playing the language game here in my head and connecting this. Okay, give me only the values of x where the value is 3 and ignore everything else. And so we're filtering things out. So we'll say select x where x is less than 0. Well, that's x where x is less than 0. And there's nothing. We have empty array because everything's been turned off because it's an array of falses, right? Let's keep going. If we say select x is greater than 3, well, x square bracket x greater than 3. So we're filtering our results here. And we get back a new array, right? A copy, like a transformed copy. X is still that original array of numbers 1 through 5, right? But we're getting back a copy when we produce this filter or that Boolean mask. And so we could say, select x where x divided by 2 leaves no remainder. We do x where x mod 2 double equals 0. And since we know this gives us back a copy, we can say evens from x, like that. So if you recall from the we had in the Python admissions test, there was a question for remove evens, where you write a function. And in base Python, or vanilla Python, however you want to call it, in base Python, this is a loop with a conditional and another operation to append to a list, or a list comprehension of some kind. check this out. If we make some function, def, remove evens, we take in some variable, and what we can do is let's return x, where x divided by 2 leaves no remainder. And other than the typo here, return. There you go. No loop, no conditional, no starting with an empty list and appending onto the empty list, no list comprehension. Why are we just so mean to y'all? I'm missing a syntax. I'm missing a comma here somewhere. It's after 20.
3 and 24.
There we go. Unsupported operand type. Oh, this is great. This is great. This was completely unintentional, but I'm going to leave this on the screen, and this is an opportunity. I want to open it up so my muscle memory knows what to do here, but I want to open it up to the class and visit with y'all. You're going to see this error. I promise you, you're going to see this error yourself. So I want to expose you to this now. Unsupported operand type for list and int. Anybody have a hypothesis on what could be going on here?
Because it's creating a tuple. Tuples are in strings, right?
Don't worry about the tuple. Yeah, we actually don't have a tuple on the screen. And the message is telling us list an integer unsupported operand type. And the operand is the percent here, right? Simple. Check this out. I'm going to provide y'all a little more context. Same function. And I'm going to send it in one of my variables from above, a. That worked.
The difference is in the first one, you're passing a list. In the second one that worked, you're passing an array.
Victory dance, victory song. Da, 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 da. Yeah. See how the function itself works totally perfectly if it's given a NumPy array, right? But if we give it a list, we can't do the percent operator on a list. Great identification of the challenge, Steve. Let's see who wants to take the alley-oop from this and help add something to the function definition that will fix this for us.
Can you just add np.array x?
Like this?
Yeah.
We can. I'm going to run the cell again. And we get the same error. And Sam, you're totally on the right track. However, we still get the same error. And any takers, or Sam, do you see it, or anybody else?
You just have to assign np.array x back to x.
Bingo. NP array makes the array. Sam was totally correct. That was like a triple alley-oop, right? Steve identified the problem. Sam went for the dunk, went and got it right, but it like bounced off the rim or something. Then David got it. It's because we have to reassign that variable. And there we go. We're rocking and rolling. And there's some like space between stuff, but that's not part of the data. That's just part of the printout, right? Part of the presentation there. Cool. That was a pretty cool journey, right? So it's maybe not a one-liner, and if we forced it to be a one-liner, it'd be kind of ugly. Awesome. I'm gonna pause because we did a number of things, we did a number of tasks, and this last walkthrough with this remove evens involved quite a bit of synthesis. and pulling in the different pieces of what you already know about Python, synthesizing what you've seen in NumPy this morning so far. So I do want to pause and open up for questions at this point.
When I put this code in that you have on line 48, I'm getting error function object is not subscriptable, but I have everything you have on there, and it's, I don't know, I'm confused.
I'd be willing to bet you that the function call might look a little different. The last line might look a little different. You certainly don't need the same exact numbers, right? We could just do 2, 3, 4, 5, 6, 7. You've got the parenthesis after the function name.
If that doesn't work, you just paste it.
Oh, I think I might see what the problem is, actually. Thank you.
Yeah. It's so weird. Like we're learning a new way of thinking as far as like thinking programmatically and thinking computationally. And at the same time, you're learning new syntax, and we're humans and we make typos. So it's like the debugging process is kind of like being almost like in like kindergarten or something. We play spot the difference, right? Spot the difference, or like double check every little thing.
Totally. Like what I find when I am first learning something new is that when I get an error, I am more likely to think it's something that because I don't know what I'm doing or something like that, and less likely to think it's a typo. And then as you get stronger in it, you'll be more likely to think like it's a typo or something. So always remember that that you could actually know what you're doing and be doing it right. So always check for the simple issues. Also, I think it's a natural process to assume it's something that like because you just don't get it or something like that.
Yeah, better to check your spelling and have a Snickers bar than like question yourself. That's my attitude. Awesome.
Something interesting that I noticed whenever you switched over the input was in the previous, like the super long list, it was kind of doing like whenever we would do our dot replace with a space, it like changed the spacings.
I have no worry about that at all in any way. This is an artifact of the output, not a property of the data. Yeah, you're talking about this padding right here? Yeah, nothing to worry about there. That does not exist in the data itself, right? If we were to say, this is Y, and then we print out Y, like I just proved it again that the output looks a little weird, but yeah, this is just a weird like printy output thing. There's no data in here that's giving us spaces at all. If we had spaces in here, this would fall on its face, right? If we did numpy.array 1, 2, 3, I'll just give this one to y'all, right? If we did X, I don't need this will create itself, right? That array will exist, but see how this one string kind of poisoned the rest of the data and turned all the other items into strings. So yeah, there's no strings, there's no spaces, I guarantee you.
What's the U21? Because I noticed that we had our int 64 before.
Mm-hmm. Yeah, that U21 data type, it means strings, basically. Yeah, I think the U stands for Unicode encoded string, which is a type of character encoding, which is a pretty large ricochet to talk about right now. But yeah, Unicode strings are Python strings. That's all that the U means. Yeah. Let's see. Make some intro to vectorization. So we covered Boolean masks, and these masks can get more complex. We could even write we could write our variables separately, like I did here, or like I did here, where we make a variable that holds the comparison or the filter, and then apply that. And then with vectorization is a little bit, it's kind of similar, because it's doing loop-like behavior on a list or an array, right? Loop-like behavior on an array without the loop. And that's kind of what we did above, right? With a conditional. So let's check this out. Say we have our variable x is np.zeros. Let's see, we have a variable called x that is an array of 10 zeros. Okay. This np.zeros function is really, really useful if you're doing, that's basically like a linear algebra zero. There's a ones function as well. But check out what vectorization can do for us. We can add 1 to every element in an array without a loop. We are introducing you to life post loops. Let's see. I'm going to create some random numbers. Let's see. I'm going to look this up real quick. NumPy random integer. So let's make an array of random numbers, specifically random integers. So this will be np.random.randint, and 1 through, let's see, 1 through 21. So this is, the start is inclusive, the end is exclusive. So the following line is like rolling a 20-sided die. Let's do that. We generated some number, right? Some single number. And if I wanted to roll more dice than that, if I wanted to roll, say, 10 dice, that's the third argument. The third argument is the size. The number of random numbers. So I have some random numbers here, and what I'm about to show you isn't related to randomness in any way. What I'm about to show you is if we have a, let's make Python fall on its face here first. So if we took some list in Python, like 1, 2, 3, and we tried to say add 1 to everything in that list, Python falls on its face, right? How would we make in Python, how would we add 1 to every item on this list? Well, we'd probably do some sort of list comprehension, n+1 for n in A. Right, but that's caveman stuff. That's cave person stuff. And we are living in a brand new world. Check this out. With something that's a NumPy array, like our variable x, we can just do +1. Adds 1 to every element. We can take our array and divide it by stuff. That's kind of wild. So what's going on is NumPy is doing the equivalent of looping for us. What if we squared everything, every element? What if we took every element, squared it, subtracted 2, and added 3 times each element? It just does it. No list comprehension, no loop, no starting with an empty array, etc. And our original array is still X. So if we wanted to hold the results, we assign these to a new variable. Right? That's pretty darn wild. And that's really intuitive, right? It's intuitive to take a list and multiply a list of numbers by, or take an array of numbers, multiply that array of numbers, or add something to it, or subtract or divide it. This kind of vectorization, this exists in spreadsheets, right? If you run a formula on a spreadsheet column, there's no loops, right? I mean, I'm a real big fan of programming languages, and you know, there's spots where spreadsheets aren't the right tool, but they have that right. They have the vectorization right, and NumPy is like, oh, that's a good idea. We need to do that. And if you look at what we're doing with multiplying arrays and stuff by scalars, like this kind of notation matches what you'd see in a linear algebra book. Right? We can add arrays, right? I did array multiplication. I did scalar vector multiplication. I'm doing vector addition. We can do vector subtraction and scalar multiplication and vector subtraction, right? Pretty wild. Pretty wild. I'll do one more little. Let's see. I think it's just dot. We can take. There's many more linear algebra features than we have time to get into. P dot, we could take a dot product, right? Or we could take a norm of a vector. I'm typing norm wrong. Norm of a vector. Gotta look that up real quick. I forgot a thing. Linalg dot norm. Pretty wild stuff, right? Cool. The big thing here is that we are moving farther and farther away from base Python, and we're able to do more. We're able to accomplish dramatically more results in dramatically less code with dramatically less time. That's what we're up to here. Right. Awesome. Awesome possum. How we doing, folks? Y'all doing all right? All right, cool. So we've covered quite a bit of material, right? We talked about how to create arrays. Once we have a NumPy array, we can use built-in functions on it. We've got an example of that. That was the first handful of examples. And then the last two chunks of tasks that we did, we worked with vectorized operations, which is just taking mathematical operators that usually work only on single numbers and applied those to vectors, applied those to arrays, right? And then we learned how to use our comparison operators. Oops, excuse me. We learned how to use our whatever operation that we needed to do to run and get a Boolean, like comparison operators. We use that to filter our results with that array of Booleans. You'll hear the array of Booleans. You'll hear this called, like I said, Boolean masking, array filtering, or indexing. Because we're getting at the indices by means of an array of Booleans that tell us which values to turn on and turn off as part of the output. Right? In a way, the Boolean, the array of Booleans here is is giving us the filter, right? It's how we're filtering that array. And if everything matches, we get the exact array back. If nothing matches, like this array didn't have any negative numbers, we get back an empty array, right? So I'm not sure about y'all, but I would much, much, much rather have x plus 1 and read x plus 1 than something like a loop, this little 5-line here, right? I'd much rather take this original array and just do plus 1. Turn it into a NumPy array, rather. Yeah, you're gonna see this error over and over and over, type error, type error, type error. Folks, if you're seeing errors, it means you're making progress. It may not feel like it, but the only people who have no errors are the people not writing any code. So what I'm going to do is I've got to turn the original array into a NumPy array and then add 1 to it. There we go. Not too shabby. It is totally possible to have other data types and have like NumPy arrays of strings. We're probably going to do much more of our string work in pandas because pandas is like NumPy on steroids. But like if we had the Beatles here and made a NumPy array of the Beatles, let's see, Matthew, Mark, Luke, John, Ringo, George, Paul, and John. And then we could say, with this array of Beatles here, we could do that same kind of operation where who in here is Ringo when we get the array of Booleans, and we could say Beatles, where Beatles, we could say is not equal to Ringo. Beatles, there we go. Right, so we're generally just doing a lot more math and numbers in NumPy, right? It's not StringPy, it's NumPy, but we can have some operations there. It's not totally out of control here. Right, so we can say give us everybody but Ringo, give us only Ringo.